homotopy groups aren't going to teach themselves, huh?
I'm not sure if I'll even teach them, so...
No. Well, I want a refund.
Ooh. Okay. Alright guys, let's start with the word. Dear Lord, just thank you for this day, and thank you for bringing us here today, and for the opportunity for us to study more of algebraic topology. Maybe we'll just have clear minds and be focused and be able to understand these things. And just know, right? Amen.
Amen. Oh, that reminds me. In terms of the final exam week schedule, I still haven't decided when we should meet, but we shall meet.
Well, wait, do we have a final in capstone?
We're supposed to.
Okay. Actually, I didn't look for
That's
that.
right.
So
I have to give you guys a final.
Well, you don't have to.
Yeah. You don't give us a final, that's more time I can spend honing my letters of intent for grad school.
Well, come on, the final final for your capstone course is more important than that.
Do some cute calculus problems.
See, I still don't know what to say about your letter just yet. But anyway, we shouldn't talk about that now.
Alright. So we kind of stopped at the last time, kind of defining what
page are we on?
We're on...
Because I'm on the wrong page.
336, I guess. 334 is where the homotopy groups start. We kind of define what they are.
Excellent. Oh, yes.
So see above, and I'm just kind of going to go through it and find just some like different theorems that we have to kind of understand how these relate to each other, at least in some contexts. So on 336, 337, 338, kind of goes to a really strange argument that honestly I didn't really pay attention to, so we're going to skip it.
Okay.
We kind of get this idea of a local system that is a family of groups with a family of homomorphisms with certain properties that it preserves. And we see in, let's see, theorem 11.24 that if there is this local system of a path-connected space X, then the homotopy group is going to be the same no matter what base point you're looking at. So we get there. Yeah, so if X is path connected and there exists a local system, then we have pi n of X comma X naught is equal to pi n X comma X1 for all X on Xn with the X. Okay, that'll help us to figure out some other stuff. And lemma 11.25 tells us that if we have a free homotopy, let's see, I'll just write that. Using this, we have F being witness to the homotopy between F and G, where, you know, F and G are maps from X to X. And right, and we let's see. Sorry. So we get this convening diagram. Pi n X, comma X naught, F star. Then do some map with pi n X, comma F of X naught.
What was a free homotopy?
It's just a regular one.
Oh, just a regular one.
And so we're able, and so if we have X comma G of X naught, then we get this for each phi, let's see, where we define phi of X. Let's see, phi of T, I guess, is equal to F of X naught comma T. Then we get this family.
Daniel, before I forget, in problem 14 in the assignment, is supposed to be 0 less than or equal to p less than or equal to n. I have p equal to 0 right now,
Okay.
which was concerning to Nathan for good reason. Sorry, I should
Yeah. Sorry. And so we end up with this.
I was closing the
Local
window.
system,
It distracted me.
And so, kind of as a corollary to that, we have that if
So he's using the free homotopy to construct a local
yeah,
system.
yeah. So we have a homotopy equivalence f from x to y, from x to y.
Ah.
F star from pi n x comma x naught to pi n y comma f of x naught as morphism. This helps us define isomorphisms between some of these homotopy groups. Another corollary is that if these are both path-connected spaces, then for every, let's see, corollary 1.27, x, y, path-connected. With same homotopy type. Then for all x naught and x, y naught and y, and pi n x naught is isomorphic to pi n y comma y naught. And proof is really easy because it you can kind of go through using the last corollary, getting from pi n of x comma x naught to pi n of y comma f of x naught. That makes it an isomorphism. And you can get from that to pi n of y comma y naught using this one, since we have all the tools that we need for that. And then another corollary. 28. If x is contractible, then pi n of x comma x naught equals 0 for all n. This last theorem is also for all n. And that's because if it has the same homotopy type as points of then pi n is 0, and so they have the same homotopy group. Okay. Then some of these arguments use covering spaces, and we didn't cover that chapter, so I'm not going to talk too much about it. But we also got other theorems, like 30. So pi n s1 is equal to 0 for all n greater than or equal to 2. Let's see, 11.31.
But basically what 11.29 says is that the fundamental group of the covering space is the same as the fundamental group for the space which is covered. Well, not just the fundamental group, but
Right,
all the higher homotopy
yeah.
groups as well.
Yeah, makes sense. And then we also have 0, q between 0 and n, then iq of Sn is equal to 0.
Oh yeah.
And pi n of Sn is not equal to 0.
That's the proof of 30 then is really cool, right? Because like, I know, like you said, we haven't talked about it,
Yeah.
but the real line is the covering
Yeah.
is the covering space of the circle.
That's contractible.
So since it's
Okay, yeah. Should pay a little bit of attention to that.
that's pretty.
Then he does a lot with exact sequences, and I kind of wanted to get to the fibers, so I didn't talk too much about it, but he does define a mapping fiber, which he mentions later. We can talk about the fibers. So define that.
Oh, see. So now we're talking about this section about exact sequences in not in homology. Right? These are where? Oh, just in sets.
Mm-hmm. This mapping fiber is a space. What is space? Associated with the mapping. So we got MF is equal to the space of x comma omega not omega. An element of x cross y to the I, which is, remind you, all the homomorphisms from the unit interval onto y, or into y, such that omega of 0 is equal to y naught, and omega of 1 is equal to f of x. Okay, and it says this base point is x naught omega naught, where omega naught is the constant path of y naught. And yeah, so this will show up later when we start talking about fibers. And we found a lot of exact sequences when we're talking about these bases. But okay, so now we're getting to fibrations.
So the y upper I is functions from the unit interval
Into
to
y.
y. So omega is a function
Mm-hmm.
such that 0 is y naught and 1
It's f of x.
is f of x. Okay. So the y naught is given because it's a pointed space. And the x naught is given. What's he do with x naught in that?
It becomes the base point. It becomes part of the
Oh.
base point for MF.
Oh, right. I see.
Alright, so now we get to fibrations. Or we're gonna get to that. I'm picking up some good fibrations here.
Nice. You just earned your A.
This isn't a class on puns.
Certain puns, if they reach a certain level, demonstrate a certain understanding of the topic, which cannot be ignored.
Okay.
Sometimes you're just listening to a comedian, and you're like, "Wow, man, I wish he'd turn his mind to algebraic topology. I'd like to see what he could do." You always hear a certain joke.
Okay, so first we're defining what the homotopy lifting property is. Because that's part of the definition of fibrations. With respect to a space X. If for every pair of maps f tilde from x to e, g from x cross I to b, for which p goes with f tilde is equal to gi, where I
Laughing at the witch's hat. Right.
what's the opposite?
What definition is this? I know you skipped a few diagrammatic.
It's the first one in the fibrations part.
Oh, okay, I got you.
What page?
355.
Okay.
He has collapsed the diagrams. Let's see here.
Exists a continuous map G tilde these triangles commute.
It will be seen that the fibrations determine exact homotopy sequences. Proof of exactness is an application of the Hoope sequence. The theorem of Milner. Puppy. A theorem of Milner states that there is an analog to the Eilenberg-Steenrod axioms for homology that characterizes homotopy groups. Huh.
Okay, so if we have this this mapping P from E to B, and we start with these functions f tilde and g,
Right.
and this I here that maps x to x0 and x comma I, and then there exists a map G that makes these commute, I guess, with this, because it's all the same.
If all that goes, then we say that the map P from E to B has the homotopy lifting property with respect to the space X.
Alright,
You have to be able to do it for every two maps. Tilde and G.
Alright, now we define a fibration. Map P from E to B. Fibration. Or a curved fiber space if it has homotopy lifting property, HLP, with respect to every space P. I'm sorry, every space X. If point B naught is an element of B, then P inverse B naught is called a fiber.
How is the space X related to E and B here? Is he assuming something from the notation here?
I think so.
Or is it just that this has to be true for any
Yeah, I think it's for any
space?
Right, I
of
think
a
in
map.
the definition it's only for a particular x, so here they're assuming for any. Right, like the definition, it's the homotopy lifting property with respect to a space x.
Yeah.
Right.
Whereas for this next definition, it's for any space.
Any space, yeah. But this could just be any space. I don't think it relates to E and B in a particular way, except with these functions. F tilde and G. Okay, so we don't really talk about covering spaces, but the covering projection from the covering space into the actual space is a fibration. Other examples, if we have E equals B cross F, or if there's some space, then the projection P from E to B, defined by P of B comma X is equal to B, is a fibration, or B is an element of B, X is an element of F. G, that would be the vibration. With fibers.
So it's just
Fibers F.
a little bit of terminology that I think is probably worth just injecting. You don't need to write this down, but in the start of chapter 10, we defined that x tilde and x are topological spaces. If you have a mapping P from x tilde to x continuous, an open set U and X is evenly covered if the inverse image of U is a disjoint union of open sets Si and X tilde called sheets, with P restricted to each sheet, a homeomorphism for each I. It gives a definition. X is a topological space. Then the ordered pair X tilde comma P is a covering space of X if X tilde is path connected, topological space. If the mapping P from X tilde to X is continuous, and if each X has an open neighborhood U equal to UX that's evenly covered by P. So that's when you talk about covering map, you're talking about such a P. It's a mapping from a path-connected topological space to the space you're looking at.
So we can define this this G tilde that gives it the universal lifting property as follows. So G tilde of x comma t is equal to G of x comma t comma q composed with f tilde of x, where q is kind of like the opposite projection. And so we'll see that, so G tilde goes like this. So P composed with G tilde is just going to give the first parts, which is going to be G. G tilde composed with I is going to be, what do we say, I maps to x0, I think. So G of x, so G tilde of I of, this is kind of, I don't know why he talks about x as an element of f and x as an element of x. I guess it's kind of frustrating. I guess if x is on the right side, then it's an element of f, and if it's on the left side, then it's an element of x. X is going to be G of x comma 0, comma f tilde of x. I'm not sure if this can really help us too much, but let's see. Sorry guys, drawing a blank here. Q f tilde of x. Which is going to be equal to f tilde of x. I'm trying to see.
So which is the, what are you trying to confirm?
It's not the G tilde composed with I is equal to f tilde.
G tilde. Let's see here. So we should look at G tilde of I of x, I suppose.
Okay.
And then I of x is equal to x comma 0, is it?
What'd you say? Oh yeah, I of x is x comma 0.
Comma 0, and then you gotta feed x comma 0 into your G tilde function, which gives you G without the tilde of x comma 0 comma q f tilde of x.
Yeah, I guess at some point you probably need to know what G and f tilde are. Anyway, it's just an example. So
Well, I'm just curious.
yeah, me too. It's just up here. I'm not really seeing
The G must be the mapping Bx goes to B. No. Well,
it. The thing, it doesn't really specify it. So
yeah. Huh.
yeah, but another important thing is that P inverse of B is going to be equal to this B comma, well, let's see, B cross F for all B and B.
Yeah.
That's
I think there's something. I kind of agree with you, Daniel. I think there's something missing here.
yeah, I don't really see it. That's not super important. Okay, so we get 11.46 tells us that if we have a vibration, pointed spaces, where F equals P inverse of B naught is equal to F, then F has the same homotopy type as this fiber space that we had talked about, or the mapping fiber, MP. Okay, and that allows us to find out properties of some of the fibers that we have. So theorem 11.47. We have so P of vibration and B1, B9, B1 elements of B. Then P inverse these fibers, P inverse B naught, P inverse B1 have the same homotopy type. And that follows because each one's going to have the same homotopy type as the mapping fiber, and the mapping fiber's the same for both because it's the same vibration. Okay. See, trying to pick out what's important. I think the fiber product is super important. Okay, locally trivial bundles are important, so I'll get to that hopefully. I don't think I'm skipping anything too important. Definition.
Oh no. What? I just realized the mic is set at 40 instead of 75 like usual. This one's gonna be quiet.
Oh, sorry guys. Maybe I should just start yelling. A local trivial bundle with fiber F is a map P from E to B, very similar, for which there is an open cover. V, someone I don't know what that. Of B, and homeomorphisms.
Where are you?
363.
Oh.
From B cross F to P inverse B. For all V, an element of this element of this open cover, such that P composed with phi v of v comma x is equal to v for all v comma x element of v cross f. And so pretty much, let's see.
So
There's just
locally-
kind of this simple property of these.
Locally trivial bundle, bundle. You have a map from the total space E to the base space B and open cover V, which is homeomorphisms of the Cartesian product of V and the fiber to the inverse image. And also the projection of the local trivializing map composed come back to give you the point over which the fiber is sitting.
Yeah, so it's like this simple property about it. It's not.
Coordinate neighborhoods. Yeah, see, when I think about a fiber bundle, I'm thinking about this. I think the things before this
Right.
are, well, to me, they're more exotic because they're actually, you know, I've heard these things before that algebraic topologists use fiber bundles to do topology, and I was like, what? I think it's because I don't appreciate the deeper and less trivial kinds of bundles. Pun somewhat intended. Although this doesn't have to be a trivial bundle, this is locally trivial. Right? It just says that locally it's like a Cartesian product. It doesn't say globally that's the case. So,
Right.
but this condition that it be locally trivializable is pretty huge in terms of how the coordinates have to behave and stuff as a manifold. It's pretty simple.
And then going back to the example we had before, we can show that the vibration we had here leads to a trivial bundle. So
Using
for a locally trivial bundle.
ah.
Alright. Okay, then we get to the hop vibrations.
So the covering space is kind of a silly bundle,
Mhm.
right? It's just some sort of discrete space, pieced it over each, glued over each point. Right? The fibers are discrete, homeomorphic discrete spaces.
Right. Yeah, that's something I forgot to mention before. Right, and so in another chapter that we skipped, chapter 8,
Yeah, go on.
it talks about
Man, you guys
complex
got a lot to
and-
do. You got a lot to do in grad school. You guys got to get to it. All this material we skipped. You got to get to work. Tell you what,
We only
yeah.
skipped like 2 chapters though. That's actually not that bad.
Yeah, I guess.
But yeah, but even within the chapters, we skip some stuff.
Yeah.
So on page 183, in one of some of the exercises, he defines some projective space, or
Ah.
that there's a complex projective end space and a quaternionic.
Hey, that's in your homework. You got a question about the homology of CPN. It's in there.
Where CPN, where if you define a relation on the 2n+1 sphere,
I hear that quaternionic end space is really hopping.
okay, this equivalence relation where x is equivalent to y, if x is equal to lambda y, where lambda is complex. And
I love this paragraph on page 183. Some of my favorite formulas. It's amazing.
True. And then pretty simpler. So we got C. Pn is going to similarly, we have HBN. Isomorphic to S, I think 2n plus 1. Oh, 1 plus 3. A similar equivalence relation where x is equal to y if x is equal to lambda y. Finish the same thing. Where lambda is a quaternion now. And
Oh, right. Oh man, where have I looked at these before? These are really cool. Dang it, I'm trying to remember. Were these in Taft's book? When we did the matrix groups the other summer, did we touch on these? I don't remember. It's not far from it, right? Because we look at the like the inner product and the real inner product or the complex inner product or the quaternionic inner product, and then you obtain the isometries as the orthogonal groups, respectively, of like the real orthogonal group or the complex orthogonal group, or and it becomes a symplectic group over the quaternions or whatever. And then inside that context, you can still, I think you can recover the spheres in some way, right? Like, how do you get spheres from the orthogonal group? Is that the homogeneous space stuff? How do we get?
sounds right. Let's see.
Anyway, I'm
Yeah,
distracting
sorry.
you.
Yeah, okay.
So complex
So-
projective n space can be viewed as the antipodal equivalent. Is that the antipodal equivalence? You got x is equivalent to y if x is equal to lambda y for some unimodular complex number.
It's not quite antipodal.
It's more than that, huh?
Yeah. It could be. But it's not necessarily. Kind of depends on what lambda is, I think.
So that's like it's saying there's a circle, right? Like, is that fair? Is it a circle?
That's what
For complex numbers, I think
Yeah,
so.
I'm trying to visualize what that is. Like, oh, it's hard to visualize. Dang it. N is at least 1, isn't it? Yeah. If n is equal to 1, we're already looking at some sort of equivalence on the 3 sphere. Seems like that's saying the 2 points are equivalent if they're on the same circle. What does that mean? Well, where's this copy? Oh, I know what it is. Here's the question, really, Daniel. S2n plus 1 is sitting inside what space? That's a subset of what?
R2n plus 2. Or
What does it mean then to say lambda element of C x is equal to lambda times y, lambda's complex number? See, we must be looking at the n plus 2n plus 1 sphere as sitting inside some complex space, right? I think he explains here, if I just read.
that'll definitely be reasonable. Because R2n plus 2 would be homomorphic to C n plus 1, right? And the same with
So it's a subset of C2?
well, it depends
Well,
on what n it's, right?
I mean,
Yeah.
C2n. Yeah,
This
there's
would be like a subset of C.
C2. Is it
Like at the
C2n?
n plus 1. Yeah.
Cn plus 1, okay, and then
Right, whereas this is a
and what is
subset
the n 2n plus 1 sphere inside Cn plus 1? It's the modulus, you know, the complex norm equal to 1 in there. That's the 2n plus 1 sphere in there. It's like modulus of the n plus 1 complex vector.
Wait, what? Sorry, can you repeat that?
So I mean, if you, well, I mean, it's dumb, but I think if you look at C n plus 1 as R 2n plus 2, then the Euclidean norm there, right, sum of the squares of the components being equal to 1 gives you the 2n plus 1 sphere, right? So I think that, if I understand correctly, just translates into the modulus of the, not, I mean, it's the,
Yeah, sorry.
let's say the modulus squared is the sum of the modulus squared of the complex components in Cn plus 1.
Right.
And in that, it's in that context that we have x equals to lambda y. So x and y are complex vectors. So, you know, to gain an intuition for that, you have to come to some understanding of what does it mean to multiply a complex vector by a complex scalar. I mean, they're like complex collinear or something, but in terms of real geometry, well, eh. And then, so the other one is using quaternionic n plus 1 space, which is real for n plus 4 space, in which case you obtain the spheres of dimension 4n, 4n plus 3 spheres. This is part of Hop's stuff, so yeah?
Yeah.
Yeah.
Right, and so if we define these fibers P, P of x1, x2n plus 2, which, you know, you can kind of write P of z naught, zn, right, because this is,
What page are you on now?
now 366.
Okay. Sorry to interrupt. All these questions and more would have been answered by the formulas here anyway.
Yeah, that's true. Right, where in this case, j is going to be equal to x2j plus 1 plus I times x2j plus 2. Right, so we can see r2n plus 2 equivalent to cn plus 1. Right, and then we have this sorry, forgetting the word, equivalence class within this complex projective space. Okay, and then similarly we have Q, same way x1, x4n plus 4, which is going to be equal to Q of h naught, hn, which is going to be equal to the equivalence class again.
You actually, when you actually look at the proof that the trivializing map, you know, composed with the Hopf map, Hopf vibration map, the Q or the P, gives the identity again. Or is it the identity again? Are you going through the proof of 11.353 or no? I'm not sure where you are. Yeah, this formula is neat, right?
Let's do that. So P and Q are called the Hopf vibrations. Okay, so let's get to this theorem.
You can
of the hot vibrations are locally trivial bundles with fiber.
I was just reading the last sentence in this book, page 14. It ends with, "You are now in the hands of J.F. Adams." Like, is that the book that comes after this book? It's a funny thing to say. Sorry.
I would like to know a book that goes more in depth into cohomology.
Yeah.
Because
I may not
from what I've looked up, there's a lot more to it than
Yeah, I
this
think I'm
chapter.
probably not following that chapter, in all likelihood. I must.
It doesn't even talk about de Rhomb's theorem.
Yeah, I must consult my other cert. I got Bottom 2 up there. Got a few other things to look at.
Alright, so we start with showing that P is locally trivial. We know that then. The proof for Q is similar, which I believe. For each J, 0 less than or equal to J less than or equal to N, we define Vj is equal to the set of equivalence classes Zn, which run into this projective space, such that Zj is different than 0. Okay, it says each Vj is open because its complement is the image of a closed compact subset of Sn f2n plus 1.
So remember we talked about like real projective space, or like the coordinates on real projective space is a manifold somewhere once upon a time.
Mm-hmm.
This is just that again. It's like, so you can divide by that J thing.
Mm-hmm. From Vj across S1, because we're trying to show that S1 is a fiber.
Yeah.
To P inverse Vj by kind of following the Vj of Z naught Zn comma U for U element of S1 is going to be equal to modulus of J of Zj.
So it pulls out this scalar factor in the front. Get the Zj times U divided by
Square root of zk squared, which is basically like the norm of the complex vector,
right.
which is non-zero times.
Sorry, I just saw it work. I saw how it works. It's cool.
I'll just put the 1 over Zj in the front.
So for complex n space, right? Like we usually have that for like a real norm, you can pull out the absolute value of a constant. So for complex n space, you can pull out the modulus of the constant, right? And he's got that Zj inverse appearing multiplicatively in each component. And of course, the modulus of Zj inverse is 1 over the modulus of Zj. You keep writing. It's easy. You got it. Exactly what you just did. And you got to take them.
Because it.
Just take the modulus of that, and you can see that it comes out to the modulus of U, because the Zj's cancel, and the modulus of that n vector is exactly what you have down there. It's the square root of the sums of the squares, the moduli of the components of the n complex vector.
And it's well defined because if two points are equivalent, the multiplying by lambda kind of cancels out.
Oh, right.
This.
It's like.
Then the map.
See, this is a good Math 200 problem. Show this map's well defined. Yeah.
P inverse V1 to V1 cross minus 1.
It's a monster. We could put n equals to 2.
Given by
For the honors students, we'll put n equals to 3.
So we have this map, this inverse map. Let's see, given by z naught, zn maps to its equivalence class, and the normalized zj.
Man, engineers are angry when they calculate.
So that tells us that phi j is a homomorphism.
I feel like he's trying to bully the students into calculating something. You will analyze this circuit.
All right, so that tells
It'd be
us
funnier
that
if the camera actually picked some of that up. Of course it doesn't.
yeah. So that shows that it is a locally trivial bundle, and the S1 is in fact the fiber, and similar result. Similar to prove for the
Yeah.
quaternionic projective space. Okay. So these corollaries. This is 11.54. So we get some concrete results for low-dimensional spaces. So we have pi n of S2 might be equal to pi n S3. Oh, part backwards, but it's the same. For all n greater than or equal to 3. And another one, doesn't look like too much, but it's still pretty interesting. Pi n of S4 is 2 pi n minus 1 of S3 for all n between 1 and 6. Alright, we get another one that says that proof of that uses some of the stuff that I skipped, so if we have time at the end I can go back and look at weak fibrations and look at that if you guys want. See this? Pi 3 of S2 is non-zero, and that's pretty simple because we already knew that pi 3 of S3 is going to be non-zero, and we just showed that it's homomorphic to pi 3 of S2. Well, it's not exactly something I could have guessed. That's why. Yeah.
So these are kind of special. These kind of links, like S3 and S2, and
Right, and these special ones that are specifically these
S4,
lower dimensional ones, yeah.
S4 and S3.
I guess that's about all I had for you guys. Afterwards, he just kind of talks about, I guess, where he's going to head in chapter 12.
Yeah. I mean, these examples, of course, are important for just kind of comparing and contrasting homology with homotopy. Like this example 11.14, basically he gives an example of spaces X and Y that have isomorphic homology groups that have different homotopy groups. So he looks at the join of the 2-sphere and the 4-sphere, and he lets Y be complex 2 space. He argues that they have the same homology for all n. In particular, the homology is the integers for 0, 2, or 4, and it's 0 otherwise. But then he argues that S4 is a retract of X, and so the pi 4 of S4 is a retract, a direct summand of pi 4 of X, and so the fourth, I don't know what to call this thing, the fourth homotopy group, I guess, of X is non-zero. On the other hand, since there's a locally trivial bundle, the 2n+1 sphere to CPN with fiber S1, the theorem 11.51, which was, where was that? So the homotopy sequence of a weak vibration. Yields that the qth fundamental, qth pi, so qth homotopy group of the 2n+1 sphere is isomorphic to the qth homotopy group of CPN. So it follows that for all q greater than or equal to 3, it follows that let's see here. So in particular, the fourth homotopy group of CP2 is isomorphic to the fourth homotopy group of S5. So he argues that pi 4. So he had before shown that pi 4 of X was not 0. So now he's got that pi 4 of CP2 is 0. So obviously, the homotopy groups of X and Y here are not isomorphic. Albeit, even though the homology groups are isomorphic, so. And then he goes on to give a list of other things which break for homotopy. He says, in particular, there's no exact homology sequence. Excuse me, there's no. How to say this? They need not vanish in degrees above the dimension of the space. There's no exact homology sequence of a vibration. There's no excision for homotopy groups. It's an example. And then he mentions that Milner has some result which is analogous to Eilenberg Steenrod for homotopy, I think. Which involves exact sequences and sets. So. He talks a little bit at the end here about what the great beyond, generalized cohomology theory and so forth. So you wanted to go back? I don't know if we have.
Yeah, I'm not sure if that's really necessary.
Not necessary. Yeah. I'm not sure I have time.
Yeah, it's not.
Better not.
Doesn't take too long to find out what a weak vibration is.
Yeah, so I'm not sure where I should pick up for. I'm going to try to say something about cohomology in our next meeting Thursday, and then the meeting we have.
Something like this week.
I'll try to bring something together, say something useful.
Mm-hmm.